Okay, Kim, 115 students, it's time to talk about titrations. Since there wasn't as much time as hoped to discuss this in class today, I hope you find this helpful, although it should be very much like what you did in the laboratory in the titration of vinegar for those who are in the lab. So let's talk through these questions. Hopefully you follow along in your book on Chem Activity 32 to do this. So here's the representation of the reaction of acetic acid with sodium hydroxide is shown here. Acetic acid, as I mentioned, has more than one way to be represented, which makes it confusing. But CH3COOH is the alternate way to write that formula. It means the same thing as this one shown on the left. It's shown this way to show an acid proton in the front. Reacting with sodium hydroxide should be a neutralization reaction. Acid plus base should make water and a salt. So is the reaction shown balanced? Count the atoms. Well, there's one sodium. I'm looking at the easy ones. One sodium. And if you look at the acetate ion, which is everything except for that hydrogen in the front on the acetic acid, there's an acetate ion on the right as well. And then the remaining part of the reaction is simply the reaction of hydrogen ion with hydroxide ion, which is the essence of the neutralization reaction, which combine to make water. So far, so good. It's balanced. What kind of double displacement reaction is shown in this model? Well, guess what? That's what we call neutralization. And so when you add an acid plus a base, looking at the cations, the anions, you can put them together to make new products, and you get water and some kind of a salt in this type of example. As long as you're using metal hydroxides as your base, you will get water as your product. All right, now, what are the chemical names of the two reactants in Model 1? Well, the first one is shown up above is acetic acid, and it takes a minute to write it, but there you can see it. Acetic acid is the leftmost reactant. Sodium hydroxide is the second one. You should be able to recognize that, so I'm just not going to write it. I'm going to circle it for you and show you that that's what we have here. And the products then are water. Well, I think you can spell that one, so I won't for you. But the first one listed, is sodium acetate. And this contains the acetate ion, whose formula you find clumsy, understandably so, and contains the conjugate base from acetic acid, sodium acetate. All right, apologies for the slow writing tool. Now, looking at this model shown in this example here, what is being described? They're measuring the pH on the vertical axis here as a function of how much sodium hydroxide has been added. And you're adding it to what? Well, apparently we're adding it to acetic acid, a certain volume of acetic acid that has an unknown concentration. And we're adding portions of the sodium hydroxide. And how much you add apparently is measured in milliliters here. And they measure the pH with each addition. So if you watch the graph, as you add more and more sodium hydroxide, the pH gradually increases from starting at the low point here, because you've got acetic acid to begin with, so that should be acidic. So it starts out somewhere around almost pH 3. And gradually it keeps increasing as you add more sodium hydroxide until they stop adding it by milliliters and they added a little bit more because it was feeling too slow probably. And all of a sudden they get to a point where the pH changes less gradually, but all of a sudden very dramatically. And if you look at it, the change in pH is small for each milliliter added for quite a while here. But all of a sudden at 23 and 24 the change gets bigger, and 24 to 25 the change is even bigger, and then 25 to 26 we have quite a big change. So if you look at that in the graph over here, it represents this middle point in the graph where there's this large change in the pH. So suddenly you reach the point where the pH has changed dramatically for a very small addition. So the point is to figure out what's happening here. The equivalence point is described in a neutralization reaction by where you see the steep rise in the graph. I'm trying to move my tool here, sorry. The steep rise in the graph on either side of a data point. And so the sharpest change in pH there is that. So circle the point in the graph on model 2 that is the equivalence point. I believe that I did, but I'll go back and verify that I did. So the equivalence point is here. Unfortunately, flipping back and forth makes my lines go away. And at what pH is the equivalence point of the titration in model 2? Well, go back and look. So what pH is that? Apparently, this point, whoops, back it up. The point where you have the equivalence point is approximately pH 9, probably. So it's close to it, this one here. And how many milliliters of sodium hydroxide were added to the solution at the equivalence point? Well, go back and look. So this is about 9. I keep forgetting I have to check my tool. About 9. And so how many milliliters of sodium hydroxide at that point? Well, apparently that was 25. So where we had that value to the equivalence point. And so we can fill that in here. And what was the concentration of sodium hydroxide added to the solution? Reading from the chart, the volume of the concentration of sodium hydroxide added is described to be 0.1 molar sodium hydroxide, so we'll fill that in here. And 0.1, and more zeros than that, more sig figs. And so using those answers, what can you determine? Using molarity and the volume of sodium hydroxide, you can determine the moles of sodium hydroxide that were added to the solution to get to that point in the titration. So the next question asks you to calculate it. So how many moles of sodium hydroxide can be calculated with those values? So you start with the entity that is not a conversion factor, namely 25 milliliters. You can't turn that upside down, right side up. It's only a right side up number. And then you're going to use molarity as your conversion factor, which as always is moles per liter. So in order to do that, the milliliters will need to be converted to liters. Put in 1 liter on the top this time and 1,000 milliliters. I hope you're good at this conversion by now. On the bottom of this conversion tool. And when you do that, it should be more obvious that the milliliters have canceled. And in order to get to moles, you're going to have to do something to put liters on the bottom. That's where molarity comes in. So molarity is always moles per liter, so put in the value that was shown in part D up above, 0.1. You can put in any number of zeros on there you want to, but they don't really help. Moles per liter. And that, having done that, the liters cancel. And now we can do a little bit of math with our calculators. 0.1 times 25 is 2.5 divided by 1,000. And that's not too tricky, but get out your calculator and verify it with me. 2.5 thousandths is 0.0025 moles of sodium hydroxide. Verify that you know how to do this on your calculator because you should be good at these two. The next question then, at the equivalence point, the base has exactly neutralized the acid. That's what titrations are for. And no extra base has been added. Considering the answer to part A, the equivalence point there, and the equation in model 1, how many moles of acetic acid have reacted at the equivalence point? Well, the point is that's where you have actually exactly neutralized. So therefore, we would presume that there should be exactly the same number of moles, and it should be what we just calculated for the sodium hydroxide in the previous step. And so the moles of acetic acid that have been neutralized at this point is again 0.00, sorry for the tool, 25 moles of acetic acid. And the value should be the same if you have neutralized it. So, acetic acid. I have written this acetic acid in the alternate formula here, not the same one as shown in the question, realizing that the way I'm representing it here is the more common way to write acetic acid. So that tells you how many moles of acetic acid were present at the equivalence point. So why are these answers the same? It's because, hopefully, when you have reached that point in the titration, at neutralization, when it's neutral, the amount of acid is going to be equal to the amount of the base, or the moles of acid equals the moles of base. And so that's what the point of a titration is to figure out how much acid, or whatever it is the unknown one is, in this case acid, is present, and or specifically how many moles of each. And so, using that information, in which step of question 5, is it A or B, is it essential to have the balanced chemical equation? And so, do you have to know this to get the equivalence point? Absolutely. So, you have to have the balanced chemical equation in the equivalence point of step B. And if you don't have that, then you don't know the ratio of acid to base, so you have to have that. Now, why is this essential? Otherwise, neutralization won't be coming out equal. Is it necessary that the pH is going to be neutral at the equivalence point? Apparently not. And so all you have to have is equal amounts of acid and base. That is the point. So equal number of moles, oops, oh boy, this is writing terribly today, number of moles of acid and base. In this particular example, it came out to be around pH 9, but if that's the equivalence point, that's just the nature of the reaction that you're looking at. So if you read the information box at the bottom of the page, and my text just went away, sorry, the equivalence point is exactly when all the acid is neutralized by the base, no additional base has been added. That's the point of a titration. So let's just think about it a little bit further. The idea is that you are looking for the concentration of an unknown acid or base by titrating it to the neutral point. And it's not that hard to do. You've seen it in lab, those of you who have enrolled in the lab. You take an unknown base or acid and titrate it until you reach an equivalence point. Commonly, it's going to be using an indicator such as the phenolphthalein, as shown in this diagram here. But in order to do this, you have to take a known amount of your unknown solution, either acid or base, and you slowly add to it measured amounts of the base or acid that's of a known concentration using this device called a burette. And from that, you wait till you observe neutralization. It's the equivalence point where the number of moles of acid equals the number of moles of base. Typically, you're going to get a color change or something, and that's what phenolphthalein does. Just barely a color change, but not beyond, is the goal. And so we'll look for that to tell us when you have gone beyond, or when you've reached the equivalence point of acid equal base. To do this, we'll use a little bit of calculation data, which isn't hard, and you rely on understanding the number of moles of acid equals the moles of base in the forms of hydrogen ions or hydroxide. You can also say hydrogen is hydronium, same idea. And to get moles, you're always using this relationship that we've seen somewhere before, that it's molarity times volume in liters. We did the exact same kind of relationship when we were doing dilutions in Chapter 9. And so typically of the values possible in this kind of calculation, you'll know 3 of them, and you'll calculate the 4th one by setting it up, rearranging the molarity of acid times volume of acid equals molarity of base times volume of the base. This only works as long as you have monoprotic acids and single hydroxide bases, but I won't give you any that aren't that way. So here's an example of one. We're asked to find the concentration of unknown HCl solution. For some reason the label has gotten poor perhaps, and you're going to use 12.3 milliliters of sodium hydroxide of a given concentration to reach an endpoint. You have titrated a certain volume of the HCl. So the volume of the acid here is 25 milliliters. The molarity of the HCl is what we apparently don't have. We'll need to figure that out from our calculation. And The volume of the base is the 12.3 milliliters. Let me write that in there for you. Volume of the base. And the molarity of the base is the 0.8. Molarity of the base. Get the right letters for you. And we'll set this up to calculate, rearrange this equation to come up with the molarity of the acid. Not hard math, and I will give you the M1V1 kind of relationship on a test so you don't have to do it by yourself. M1 and 2 can be acid and base, just like you use the same equation for dilution. This time A and B will be the equivalent to your acid, or 1 and 2. So the molarity of the base times the volume of the base divided by the volume of the acid. And pay attention to your units here. This will be a good sign that things might be all good, because we're thinking the moles being molarity times the volume in liters, but this one is given in milliliters, and we'll have to see whether that's going to matter by putting the numbers in and calculate or convert as needed. So molarity of the base is 0.8, capital M, molar, and you're multiplying that, times the volume of the base, which is the, oh boy, that's supposed to be parenthesis, sorry, 12.3 milliliters. And if you look, your other value for volume in this question is also in milliliters. And so if we put that on the bottom, the milliliters will cancel. So apologies for the lousy parenthesis here. This tool is very clumsy. And the volume on the bottom, the volume of the acid, is 25 milliliters. And so if we put this all together, the milliliters will cancel, and we can do a math problem. The math problem means get out the calculator. So the top is 0.8 times 12.3 divided by 25. Get out your calculator and try it with me. I'll pause to do mine. The value my calculator displays is 9. Whoops, I can't make the tool right. Oh, I wrote the wrong number in here. Wait 1 minute. Let me try that again. This number doesn't look right. I forgot to put the denominator in. And so if you put the denominator in, you get a better value. And so my value on my calculator shows 0.3936. Well, let's suppose we should remember sig figs. 3936, and the units should be molarity. And how many sig figs belong in your answer? Stop and think. This is all multiplication and division. And so in your values given in the question, you have 3 for the 12.3, you got 4 for the 25, and you have 2 for the sodium hydroxide, 0.8. So this should really be only a 2 sig fig number in your answer, which then, of course, will round off to point what? Whoops, 2. I'm trying to write the number for you. 2 sig figs will be 0.39, 0.39 molar. Okay, simple enough. Hopefully you remember how to do sig figs. Let's do one more just to make sure you see how this works. This time we're going to be doing a titration with a different acid called formic acid. The formula is shown here. And formic acid is going to be titrated. We're going to take 20 milliliters of this solution that we don't know about. And it's, oh, sorry, the formic acid is known. And we're going to try to figure out what volume is needed of a potassium hydroxide solution to titrate this formic acid to an endpoint. So what do we know? The molarity of the acid, that would be the formic acid, 0.042. Be very, very cautious. Wait a minute, sorry about that. My tool didn't cooperate as I intended. 0.042 molar is your formic acid. The volume of the acid would be 20 milliliters. The molarity of the base is given at 0.15 molar, and I would encourage you to always be extremely cautious to write down all of these values when you're working a problem like this, or label the numbers somewhere in a conspicuous way, because otherwise we mix them up and we put them in our calculations wrong. What we're calculating then is the volume of the potassium hydroxide. So the equation looks very much like the one in the previous example, but this time we're solving for the volume of the base. The volume of the base will be related to, and rearrange the variables instead of the numbers because it's safer than doing it the other way. We'll often make errors without noticing them if we do it the other way. So the molarity of the acid times the volume of the acid divided by the molarity of the base. Again, we'll just plug in some values and make sure that the units look good. The molarity of the acid is 0.042, and the volume of the acid is going to be 20 milliliters. I'm not going to use parentheses here, sorry about that, because the parenthesis does not cooperate well with the tool I'm using for this recording. I apologize for the weakness of this technology. Oops, I forgot M for the molarity here. Sorry about that. Should always keep our units, otherwise we don't know what's going to cancel. On the bottom is the molarity of the base, 0.15 molar. And again, what will cancel is something we should always check. The molarity should cancel, and the answer better come up to be milliliters. So we'll calculate the number on our calculators, pull out yours and check it out. I'm going to calculate mine too. Pause your recording so you can do it. The answer I get is 5.6 milliliters, and this time it comes out to be a round number without any extra digits. Is this a reasonable number of sig figs for this question? And go back and recheck the values. 0.15, that's 2 sig figs. 0.042, that's 2 sig figs, so you don't get any more sig figs than that in your answer. And so that's appropriate answer to 2 sig figs. Now, I could work an infinite number of these examples, but I don't think there's any point to it. The equations all look very similar to this. You will have equations exactly like this kind of thing with 1s and 2s instead of A's and B's when you get to exam 4. So you should be able to apply 1s and 2s to acids and bases and use them the same way. I will leave you for now. Do recall there is already a Kegger recording about common acid-base reactions. I refer you to check those later to remember how acid-base reactions work. And good luck on your homework. So see you in class.